We present AdaVoMP, a feed-forward physics property generation model that improves accuracy and resolution over our prior method work. Our goal is to predict fine-grained volumetric physically plausible property fields of Young's modulus, Poisson's ratio, and density. These are required by physics simulators, and predicting them automatically lets us convert static 3D geometries into realistic interactive 3D worlds. Our first work Wong took an important step in this direction. It was the first feed-forward model to augment any renderable 3D object with accurate properties throughout the object volume, which is necessary for realistic simulation. For example, beyond the visible surface, we accurately predict that the chair is filled with foam. Trained on multiple data sources, WOMP keeps every material and triplet palette by operating in a reduced matte VAE space. WOMP uses a sparse voxel transformer trained on a fixed 64 cube grid, which limits accuracy on detailed geometry. AdaVoMP advances property generation by moving to an effective 1024 cube resolution by generating an adaptive volumetric structure on the fly, allocating more voxels where material variation is high. So now, if you capture this Gaussian splat scene, you can run the objects through AdaVoMP and in a couple seconds get the physics property fields. This makes high resolution detailed objects like the graphics card, couch, and more interactive. A robot can now interact with anything in the scene, and the couch stays stable under gravity. The scene also includes meshes, since our method works on meshes, STFs, radiance fields, Gaussian splats, and any representation that can be voxelized and rendered. To do so, we first build SAV, a sparse adaptive voxel representation, used to encode both the input 3D object and the output spatially varying materials. We voxelize the shape, render it from multiple views, and reconstruct Dino V3 features over the voxel grid. To form the adaptive input structure, voxels with similar features progressively merge. The SAV structure is parameterized by a label for each voxel, from coarse to fine. Keep for no smaller voxels needed, delete for empty space, and subdivide for regions needing finer voxels. Next, we train the adaptive geometry transformer and adaptive material generator together. High resolution assets are encoded into a SAV, then converted to adaptive 3D latents by the geometry transformer. The adaptive material generator takes a SAV structure at one resolution and generates the topology and materials for the two cubed higher resolution conditioned on these latents. Thus, the adaptive material generator autoregressively generates each level of topology and materials. At each level, it operates only over voxels marked as subdivided at the coarser resolution. It is also trained to generate the most efficient topology for the correct physical properties. So, an object may have complex geometry, but if the material is uniform, we generate only one voxel for the whole object. The model can also mark large empty regions as delete or uniform regions as keep. AdaVoMP significantly outperforms prior art on diverse and scene geometries. For dartboard, AdaVoMP correctly preserves small details like the dots and parts of the board which have different physics material. All other methods miss this detail due to their low resolution. AdaVoMP works on complex objects like trees with many small leaves better than prior methods. For the chair and game controller, AdaVoMP does not oversmooth materials like WOMP, given its ability to generate the appropriate structure, and also does not produce highly noisy results like nerve to physics, fish 4D gen, and pucks. Further, in these additional objects, AdaVoMP consistently produces more accurate mechanical property fields than best prior art on a variety of simple and complex objects. For complex objects, AdaVoMP works very well, like the alarm clock, the large couch, or a billiards table, where AdaVoMP generates a compact, efficient structure shown in the bottom left. Notably, for simple objects like the pumpkin, AdaVoMP stops after generating only one voxel because the entire object has uniform properties. In many cases, this is more efficient than WOMP, which always predicts over 32,000 voxels. We show additional robotic simulations where the world around the robot is made interactive with AdaVoMP and robots interact with deformable objects. These simulations look very realistic due to the high quality material fields estimated by AdaVoMP. We show a variety of FEM and simplicity simulation with just meshes or with Gaussian plots and meshes. Again, the material fields estimated by AdaVoMP make these simulations look very realistic. AdaVoMP can be used with robot evaluation frameworks in ICML to aid in creating diverse interactive environments to benchmark any robot and any policy extremely quickly. Check out our paper for more details.